Hi friends, today we are going to talk about the feature engineering, standard scaling of attributes. So we know that this can be applied only to the numerical data, numerical attributes, and which could be either continuous or discrete. So the objective of today's study is to understand the impact of standard scaling over the attributes and see whether it loses any information or not. That is, if two attributes if two attributes are of different scale, are we going to lose any value? Are we going to lose? Is one attribute going to override the information of the other? And if at all, show how this data can be compressed, and we will see how it can be mean centralized. Mm. Secondly, we'll see the probability density function through that, whether there is an impact after the scaling or not. Secondly, we'll also see whether the distribution of the data when it is with respect to two attributes through the scatter plot, whether it is going to change or not. So we'll see the distribution. Secondly, we'll look at the performance, so whether the standard scaling functionality helps in improving the accuracy of the model. So we'll take two kind of example. One is for linear regression and second one is decision tree, and we'll see the impact of it. And the last item which we'll see is the impact of outliers. If outliers are present in the data, whether it is being suppressed or is it retained. So let's quickly start onto this. So I'll load the basic libraries like pandas, numpy, and matplotlib for basic plottings, and seaborn for enhanced plot. And now let's load the file which I have is social network ads.csv file. So I'm going to load this into the data frame df. Uh, we see that there are multiple attributes like user ID, gender, age, estimated salary, and so these are all my input data attributes. And the last column purchased, which is in discrete format, numeric discrete format. This will be my target label, and 0 means this user purchased, and 1 means he did not purchase. So after loading the data, we see that we see through the head that my file is loaded properly, and I can see 1, 2, 3, 4. So there are four input variables, and the last column is the purchase, which is my target variable. So let's now while I have loaded this data variable df, I'm going to slice the attributes to the only the required category. So we'll do feature selections here manually, and I'm picking up only age and estimated salary into the input, because user ID and gender, it may not be required for this, and this is for the study purpose, and we'll go with the simple files. So when we do iloc, here we are applying slicing. By this we say take all the rows and take up all the columns starting from number 2. So 0, 1, and 2. So starting from row number 2 until the end. So we have taken age, estimated salary, and purchase. So now my variable has been overwritten by these three attributes, out of which two are independent variable, while the last attribute is my target label. Let's verify the size. We see that it is, we'll have to use the function import this from sys module. And I see the value is 9744. And let's compare what is this, what is the value in human readable format. So when I do df info, the first thing which I'll compare is the size, and I can see that if I divide 9744 by 1024, I get approximately the same value as shown in df.info. So it gives df.info gives me the rough estimated size of the file. Now, what other attributes we can see over here? So the three values which we have picked is age, uh, which has got 400 uh, entries or observation, we can say. There is no null values. And secondly, they are of integer 64. Same goes for all other attributes. So, so what we see here is there are all 400 records. They are of numeric, and they are here age is being used as continuous data. Sometimes it can be used as a discrete data when it depends upon case to case. So in this case, it is being used as continuous data. Okay, now let's do a little bit more deep dive of it of the data. We'll do df describe to see the mi minimum value, the maximum value, or we can say it 5 point data. So what all things we see here is for age category, the minimum age is 18, maximum age is 60, and the mean for this is 37.7. So we'll have to keep this in mind. And the standard deviation we see is 10.5. Similarly, if we go for estimated salary, its minimum value is 15,000. Maximum value we see here is 1,50,000. And if you look at the mean observation, it is 6,97,000. Sorry, 69,742. So this is so we'll keep this in our record. We'll make a note of it. So the average range is from 18 to 60, and estimated salary ranges from 15K to 15 lakh, while the mean is 37.7 and salary is going to be 6,97,000 for this data. So uh, with the impact of a standard scaler, we are soon going to see that this plot is going to change. The whole data set is going to be compressed, and we'll be shifting the mean from 37.7 to 0. And similarly for estimated salary also it will be shifted to 0. So that's why it is called mean centralized the technique. And we'll also see the scaling, how the data is compressed into two scales. So secondly, what we also wanted to see is that the range is highly different. One is ranging between the age is ranging between 18 to 60, while the other attribute is ranging in terms of thousand and lakhs. So they too are of different scale uh, and different unit and different magnitude. So we'll see the impact if we are trying to read the observation in the same raw format. So before we jump into that, let's first split the data. First of all in X and Y, and then train and test. So here in one step we are doing it. We are calling the function sklearn.model selection, and we'll do train test split. So during training, I'll pick up, I'll drop the purchase column with axis is equal to uh, with axis as 1, that is for column perspective. In column perspective, drop purchase. So the balance will be age and the estimated salary. Let it be as X, and the Y value will be DF purchase. So my target level will be Y, and a test size I'm taking here for an example is 25% for test, and random state be 0. Let's visualize the data. Since we have 400 records, so 75% of that accounts to 300 observations in train with two attributes, and remaining when we're looking at the test shape, remaining 100 observation move into the test test data with their own two attributes. Now I'm going to make in my code, I'm going to make use of this code. This helps me visualizing two data frame side by side. So I've given a reference out here. We can see how to use this code. It's quite simple, just two-line code. Okay. So now after that, when we have loaded the extrain and test, let's see how does it look like. So and the first column shows me, and the first table shows me the extrain, and while the second the matrix shows me X test. So 300 records and 100 observations with both the columns, both the attributes. Now let's import a standard scalar, and we'll play with the standard scalar now. So the module from which we are going to pull is sklearn pre-processing. Import a standard scalar. Our object is a scalar. So in scalar, we'll first fed the xtrain and xtest data, and what we are going to take out is when we are fitting, and then after that we do transform. So we can do it in one stage, fit transform, or we can split this step is fit and then transform. So here we have taken train scaled. So with the object, after fitting, we are doing transformation of train. Similarly, for test scaled, with the object, we are doing after fitting, we are doing transform with xtest. So during the process of fit, it will do all the calculation of a mean and z score, wherein it will identify it will recalculate the new value, and when it will do a calculation of mean. It will not do any calculation once we do a transform and then provide the input of xtrain for each and every respective value into xtrain data. It will do a calculation with respect to z score. So now for a standard scalar, it will use z minus mean by standard deviation, and with each and every individual value, it will build a new table. So, by the way, what is the value of the scalar mean for this value? We can see this in the exponential format by default. So let's see what is the extrain value. So extrain, and this is now we see here extrain value is age is like 40, 32, and all this was the raw value, and the estimated salary was like this. After scaling, we can see that this value has changed into an array. So for easy visibility, we'll convert this array into a data frame by calling the function pd panda.dataframe. So same we'll have to do for train as well as test data. So make sure that please note that this is extrained scaled, that we are getting it from converting the array of extrained scaled. Okay. Now let's display both this the extrain and x scaled. Let's see the impact of it. So as we see here, this is the raw data. So it had age like 44, 32, and all this. Now if you see here, this value has changed from that scale to something like 0.58, some minus, and something around 1.3, 1.2, and all that. Similarly, for salary as well, if you see, while it was in the range of 1,000 to lakhs, now that has also changed from zero point 0.8 that to negative and positive, and around 1.8 to 1.4. So, but the number of observations are retained. The value has changed. Now let's see in detail what has actually changed. So we'll go to describe, and again we'll do the comparison. So now we are comparing the extrained describe with extrained scaled describe, and we see here that the mean, which was 38.1, it has mean centralized to 0. So now the mean has become 0. Minimum value which was initially 18, now it has become minus 2. The maximum value which was 60, that has become 2.2. Uh, and the standard deviation which was 10, now it has turned to 1. And rest all the observations like 25% data, 50% data, 75% data, all are lying within the range of minus 2 to plus 2. So this is the first impact of standard scalar. We see that the mean has drifted from 38 to 0, and same has happened for the second attribute, which was whose mean was 6.95, 69,583. Now that has also changed to 0. And again, the salary range has changed from minimum value minus 1.6 to maximum value 2.3. So all between the range of minus 0, minus 2 to plus 2. So now let's see the distribution of scaling. So when we do a scatter plot, we would I'll do a comparison of both the scatter plot here, both the attributes, and we'll see here that onto the x-axis, the first window is the first scatter plot is for data before scaling. So onto the x-axis we have age ranging from 18 to 60, and on y-axis you have the salary ranging from 17 to 1,50,000 to yeah, or something like that. And if you see after scaling, the scale what we saw in the data in df describe, here we can see through the the matrix that the value of age is between minus 2 to plus 2, with some data is spilling outside of this, while the salary range is also between minus 1.5 to around 2. So again, if we look at the normal distribution graph, we know that the value ranges from minus 3 to plus 3. Uh, so in the bell curve, and any value beyond minus 3 to plus beyond below minus 3 and above plus 3 is considered as outlier. So since we do not have any outlier in this case, our bell curve, it is all within the bell curve. So now let's see. Let's proceed. What we conclude from this two scatter plot comparison is my data distribution is almost exactly the same while the scale has changed. And the scale has changed for both attributes. So in effect, there is no distribution in correlation between these two data in terms of spacing. So with that as a conclusion, the scale has changed, but seems like no information is lost. Now let's see into the probability distribution function. How does it look like? So I'll make use of KD plot, and using KD plot, I'll do subplot and represent again onto the x-axis. I'll represent uh, age as well as estimated salary with the probability density function. And this is after scaling what is the probability density function. So in the first plot, we see that before scaling, my age has is being shown only as a single line, because now this can be clearly estimated, because while my salary is ranging in terms of 1000 to lakh, the two-digit figure will obviously be compressed within a single line. And with the impact of standard scalar, we can see that now none of the data is overriding over the other. Both these data, the variability of both the attributes are retained here, and they are ranging in probability density function. We can see it around minus 2 to plus 2 with maximum data, and maybe some data after plus 2, but maybe all within the range of minus 3 to plus 3. Okay. So conclusion is both attributes have been compressed to fit in one scale. So here on one scale, we are able to see both the attributes now. So now let's do a comparison of distribution of this data. So here we are again doing the distribution of those two attributes individually. So the age, if you see here, it is expanding from around 17 to 70 years of age. This is before scaling, and we can see that individually when we are seeing it, we can see that this has a range from -4 to uh, uh, sorry, I should say around -2 to +2. But if you look at the nature of the graph, it is almost exactly the same. So I can say that my distribution of data has not varied. So correlation was maintained. Both the attributes with respect to each other, they retained their property. And here we are seeing the individual property as well, that the age, the shape of this age or distribution of this age is also retained. So probability density function of age. Now the same thing which we see for the estimated salary. Before applying a standard scaler, the value was ranging from around 10,000 to 1.5 lakh. And here we can see after applying the standard scaler, as you see here, we are applying the standard scaler into this KD plot. Its value is again almost between -2 to +2, or maybe till +3. So this data is slightly skewed. So, but we are not going to read about the skewness of the data or measurement of skewness. Here we are focusing on the standard scalar. So coming back to the main topic is, as we see here, when we do a box plot, we can see that how the data looks like in terms of the maximum value. The 25% range starts just around 30, and 75% is around it may be 50 plus 46 something. Okay, and while we can see the mean of the age is 37.7. So this is what we saw in our data above. So the mean is 37.7, and the value is ranging from -17 to +60, and we do not see any outlier as such in this box plot. Same goes with my estimated salary. So the minimum salary, when we look at this uh, uh, in the terms of quarter distribution, my 25% data starts with around 40,000, and it goes until 85,000, and the mean salary would be around 64,000. It's near about 70. So yes, our mean salary was around 69,000, and the minimum salary was around 17,000, and maximum salary was around 1,50,000. So this is what we see, and there is no outlier in this. Fine. Now let's see the impact of scaling on this data when we apply this onto the our ML model. So first we will go with logistic regression. We'll call the function linear model from sklearn. The logistic regression. The object is LR. First we'll fit the extrained data, and then then I've picked up, I've created another variable LR scaled. In that I have fit the scaled X and Y. So after fitting the train, we'll do a prediction. So uh, uh, after fitting, we get prediction LR Y pred is my X test. Y scale pred is my prediction with the scale data. So let's see how does the prediction data looks like with without a scaling and with a scaling. So when we do the metrics and look at the accuracy score, we can see that prior to scaling, my accuracy was 68%, while after scaling, my accuracy has increased to 89%. So this is the positive side of scaling. Now, since both the data have been compressed into a scale, a common scale, and one does not over impact the other, my machine learning model can do a better calculation, better prediction with this data. So we can see the positive side of it. Now let's do an analysis or comparative study with a decision tree. So we call the module from sklearn.tree, the decision tree classifier. So we'll create the object dt, and dt is scaled in a similar fashion. So dt is my data without scaling, and dt is scaled is my data after scaling. So again, we'll do a comparison between the y pred and y scaled prediction. So after fitting, we are predicting. So we do when we look at the accuracy score, we can see that initially also it was 0.9%, or I can say 90%, and after scaling as well it was 91%. So we can see that by the observation that the standard scaling did not play much effect in terms of with the decision tree algorithm. The reason could be in decision tree we are taking one logical decision after the other. So they are not all the attributes are not accounted at one go. So there are nodes in the decision tree. At one point of time, we take only one nodes, and then at the next level, we go and choose a second level of node based upon the index gain. So now with this observation, we can say that standard escalator does not help or contribute for all the machine learning models. So in general, the standard escalator helps for all the attribute which uses Euclidean distance, like linear regression, logistic regression, the PCA, which is the most important to have or as I say, standard escalator is mandatory to be applied. While on the other machine learning algorithms, the standard escalator is not important. So like XGBoost, uh, random forest, or DecisionTree, this may not be required. So having covered this, let's look at the last topic, which is outlier. So now we know that our data has got the minimum range of 18 and maximum value of 60 in terms of age, and similarly in terms of estimated salary will be 69. The minimum salary is 15,000 and the maximum salary is 1.5 lakh. So let's see, we'll try to add a few outliers. So we are adding three observations, 5, 90 and 95 for age. Estimated salary for respective this age will be at 10,000, then 1,70,000 and 35 lakh. And then we'll also have to add the target label. To append, we'll add this data to our data frame. Okay, and let's see, since it has been appended, we should be able to see this value within the tail. So since I have executed this twice, we are able to see this entry twice. Okay, and let's see by plotting this graph. So after we have added these values, added these outliers, now we'll try to do a scatter plot between age and estimated salary, and we can see that there are three observations which has been added, and they are clearly an outlier. We can see through the visualization as well. So this will be around the age of 5 years, which whose salary would be around 1,000, and this will be around 90 years of age with the salary around 1.7 lakh. And the third observation is around 95, whose salary would be around 35 lakh. So this we can clearly see through the these outliers are clearly visible. Uh, Now we'll see the impact of applying a standard scaler. Fine. So now that we have our raw data, first we'll do a train test split in terms of x and y. We apply the same logic. We'll drop the purchase. Now we'll drop the target label, and for y we'll pick up the target label. And we'll take again a similar distribution of 25% into the testing. After this, we can see that 302. Now this value is different because that segment of the code I have executed twice, but here it is again 30. It is 403. Uh, if I'll run this code second time, I should be able to see 304. So now it has incremented by 4 plus 2, 6. So in sync with that, now this is 75% and this is 20% of my test data. So after doing this, let's do a train scaled in the similar fashion. We'll do X train scaled and X test scaled to the new data. And since we know that after after scaling this data, train and test, it becomes an array. So we'll convert that into a data frame to have a easy visualization. Okay, let me rerun this code to match this value. Okay, now we'll do the comparison again. So this time again, if we do a comparative study of X-train and X-train scaled, we can clearly see that initially the age, as we saw, was in the age of 20 to 60. Now this has its value has got changed to some decimal format ranging between around minus 1 point something to minus 1 point something. And a similar scale is applicable for standard scaler for estimated salary. So both the scale has been brought to a normal or they are common now. Okay. So after this the scaling, we can see here X-train scaled. So now let's plot the graph. So when we plot the graph before scaling, we'll do a scatter plot of X-train age with respect to X-train estimated salary, and this will do a comparison with uh, X-train X scaled age with X-train estimated salary, and this time the color will keep red. Similarly, we'll do a comparative study of a test. This was the train data. This is now test data. So we'll first put test age and test estimated salary. And similarly, this will be the default color. Let it be the default color. And the second label we'll see is for X test scaled and X test estimated salary, and we'll signify the color as a red. So here we can see that since I've executed only this code only once, so I can see both these observations uh, uh, present over here as an outlier clearly. And even after it has been scaled, I can see there's an outlier very clearly, and it is still retaining the same position. So the outlier is not suppressed. Its significance or its place value is retained. Now let me run this code once again. Now the second observation is just exactly overridden over the other, so we'll not be able to visualize it. But as such, we have okay. Since I have executed this thrice, so now we have four data, uh, 3 plus 3. So now we have totally of 6 outliers. So I should be able to see 1, 2, 3, 4, and third data might be somewhere hidden around. And same applies for my X test skilled. So it has got one observation, one outlier, and even after scaling, we can see again the same outlier. So we come to a conclusion. Now let's go back to our question which was there at the start. So when we saw that the with the application of standard scalar, any information is not lost. Data can be surely compressed, and the mean we have seen it was centralized. And if you look at the probability density function, we know that after scaling, after applying the standard scalar, it retained the same property. And when we looked at each of the attribute, they were clearly retaining the same shape, and when they were taken together, they could be visible on the same scale, while before applying a standard scale, one overrided the other one. So this now coming on to the uh, dependence, coming on the impact over the performance of the learning model, the ML model, we could see that on some models which are based upon Euclidean distance, this had a great significance, while on the other learning models like DecisionTree, RandomForest, XGBoost, it did not have, it will not have an impact. Similarly, in terms of Outlier, we could see that even after applying the standard scalar, the outlier was still the value was retained, and we could still see the outlier. It was not suppressed or not discarded, or I should say not treated. So here comes the conclusion with the impact of standard scaling on the attributes. Thanks for listening.